Welcome to our new video. Today we are studying a heat conduction problem. In particular, we're looking at the thermal Stokes layer, and I will explain soon why we call this Stokes. Okay, so we consider a semi-infinite solid. So a solid here. And this solid is at a temperature T0. We define a coordinate system y perpendicular to the surface and x that runs parallel to the surface. And this solid here is has uniform properties. So we have a K, the thermal conductivity is constant, and so are rho, the density, and the specific heat, so they're all constant. So we're considering a 2D problem, so the temperature in this space only depends on, let's call this actually tau, it's better, tau. The temperature is only a function of x, y, and t. What we have is that the temperature of the solid wall, solid surface here, depends sinusoidally in time. So we have tau, the temperature, is equal to tau 0, which is the mean temperature, plus tau tilde times cosine of 2 pi t divided by big T. So as the temperature of the surface oscillates sinusoidally, then the objective is to find the temperature at any point inside this solid. Okay, so it's an unsteady 2D problem. Okay. So of course we have to study the heat conduction equation, and the heat conduction equation for the case of constant property is rho Cp and then partial tau partial T. So this is per unit volume the change in internal energy of the solid equal K, and then Laplacian of tau. And of course this is the conduction term. So for each point in space we have a balance between the change in internal energy at that point and heat conduction. So we can expand this. Partial tau partial T equal K, and then we have second derivative of tau with respect of x, second derivative of tau with respect of y. So this is a 2D problem, so we don't have the gradients along the z direction, but since we saw here before that the boundary condition does not depend on the coordinate x here, then we can also neglect the derivatives, second derivative along this direction, so this is 0. So the problem reduces to the following form: partial tau partial T equal alpha second derivative tau with respect of y, when alpha is equal to K divided by rho Cp. So this is of course the thermal diffusivity. Diffusivity. Okay, so we have already an equation that we can integrate. So it's a PDE, and so to integrate this we need boundary conditions. But before doing that, we define a new variable tau tilde, and this tau tilde is tau minus tau 0. So we subtract the mean temperature, and so the problem, so let's rewrite the differential equation again. Alpha. So the boundary condition, so at the wall we have tau tilde at y equals 0. The function of time is tau bar cosine of 2 pi t divided by big T, which is the period of the oscillation, and then tau tilde as y goes to infinity, so a large distance from the wall, is 0, because there is no temperature tau tilde far away, because at a large distance from the wall the temperature just reduces to tau 0. Very good. So we have defined our problem. We neglect the initial effects, so we don't have an initial condition. And this is a second order problem in space, so we have two boundary conditions in space. And immediately we note then that this problem is mathematically equivalent to a very well-known problem in fluid mechanics called the Stokes second problem. And in our channel we have a related video that solves this problem. So this is of course a fluid mechanics problem, but they are mathematically equivalent. So let's see more specifically what the equivalence lies to. So first of all, in the Stokes problem, instead of the tau tilde we have a velocity u. So we are not looking at finding the temperature in that case, we're looking at finding the velocity profile. So the tau bar with the maximum temperature of the oscillation of the wall, we have a u bar. And instead of alpha, the thermal diffusivity, we have nu, which is the kinematic viscosity. And everything else is equivalent. So if there's a full analogy, and in particular we have that then the partial tau partial t, so the change, the term that's proportional to the change in internal energy at each point, and this is analogous to partial u partial t, so the acceleration in Eulerian sense. And the second derivative of tau with respect of y instead, so that proportional to the heat conduction at each point, we have partial u partial y, the term that's proportional to the transfer of momentum. So transfer of heat by conduction is equivalent in the Stokes problem, the fluid mechanics problem, to the transfer of momentum. So if you look at the video that in which we solved the fluid mechanics problem, then we saw there that the velocity profile has a certain specific behavior. We found the analytical solution. So if this is the wall, So the solution is confined in an envelope, exponential envelope. So at different instant in time, then we have a profile like this. When it's maximum on the other side, then we'll be like this. And intermediate phases, we have something like that. So this is the, in our case, is the temperature as a function of y and t. For the Stokes layer, then instead we have a velocity as a function of y and t. But since these two problems are mathematically equivalent, then we can use the solution of the Stokes problem, second Stokes problem, in the fluid mechanics case, and just use it for the conduction problem. So in our case, we have then the solution is tau as a function of yt is equal to tau 0 plus tau bar, the maximum temperature of the oscillation at the wall, times E minus square root of pi divided by T alpha times y, and then times the cosine of 2 pi t divided by big T minus pi t alpha times y. And if you look at the video on the Stokes problem, then you saw there that we found a thickness for the Stokes layer, and here we also can find a delta 99, but this will be a thickness, a thermal thickness, so that measures how far inside a semi-infinite wall the temperature effects have diffused, and that's equal to 4.6 times the square root of alpha t divided by pi. Okay, very good. So of course we can already consider, so although these two problems are mathematically equivalent, then there are a few differences, of course, we can discuss. So first of all, in the fluid case, so the Stokes second problem, we consider a laminar flow. And therefore, if the Reynolds number based on the thickness, so on the delta 99 times u bar divided by nu, the kinematic viscosity, is larger than a certain critical, then the flow may become unstable. And of course, in the conduction problem, if you have a solid, then there's no such thing. But we can encounter in the conduction problem, instead we might have thermal stresses. Thermal stresses due to the high temperature gradients. And the last comment in that in the fluid case, we computed the power spent injected into the fluid, and we found that to be proportional to mu u bar at, so at y equals 0, times partial u partial y at y equals 0 times the area, the surface area. So in that case, we have a force times the shear stress, and this, we computed this in the units of watts. But in our case, in the conduction case instead, in the conduction case, we have instead a Q. So a heat transfer rate, so this is a problem of continuously heating and cooling the wall, and of course we can compute that thanks to Fourier's law of conduction, minus K thermal conductivity AS partial T partial Y at Y equals 0. So this is in watts. So there is no like a full correspondence here because the K and mu play a similar role, but here we're multiplying by the velocity, whereas here it's enough to just consider the temperature gradient at the wall. And finally, final comment is that we can have a thermal Stokes layer also in a gas or a liquid. So we can have here the fluid, and we have the temperature that varies sinusoidally and induces a temperature gradient inside the fluid. But as long as the gradient or temperature are small, then we have no free convection, which means that the temperature gradients do not induce any velocity. So we have no U bar, so no velocity field inside the fluid. So in this case, we can still use the solution of the conduction thermal layer in the fluid case. And there is a paper by Niemela that I found on Google Scholar recently, et al. This studies exactly this problem experimentally, so the stability and the free convection inside this system, and this is published in Physical Review Letters in 1986, and this is volume 57. Okay, so thank you very much for listening, and I'll see you in the next video. Bye.